This video will talk a bit more about LiDAR, some of the more recent LiDAR sensors that are out there, and how we can use them for range finding and doing all sorts of different scans in 1 dimension, 2 dimensions, and 3 dimensions. One thing I should mention is more recently, in the last 5 years or so, there's been a number of lower cost time of flight LiDAR modules coming out. From these Pololu ones over on the far left, they've got fairly short ranges, in this case 50 centimeters. There's some that are slightly longer than that. Fairly accurate, so accurate to about 3 millimeters, which is pretty accurate sensor for a time of flight thing, and relatively low cost as well, in the order of $13. This scales up to more advanced ones, including this Benawake one, which is about 180 meters. They've got different ones that operate on different ranges, for example, a 90 meter version and 60 meter versions and things like that as well. Those ones are a bit cheaper and have higher accuracy. Accuracy here is in the order of 10 centimeters, and they're about $220 to, well, $100 for some of the cheaper ones as well, depending on what sort of ranges you want. But these are what we call 1D LiDARs, or single point LiDARs, where we've got a single laser beam that's being reflected back and we're measuring the time of flight on that single one. Well, what if we expand that? What if we move that single laser beam? What we can then get is we can scan a whole plane. We can get what we call a 2D LiDAR. And there's lots of 2D LiDARs about. Here's one that 6 made. There's a lot of manufacturers that are making these now. And this is a growing area, particularly in robotics research, because LiDARs are heavily used on the factory floor for safety systems, for robot navigation, for obstacle avoidance, those sort of things. Here, we typically pivot a mirror in an arc, and we take a whole series of measurements, maybe at 1 degree increments. And we might do this 10 or dozens of times a second to get this nice picture of what's going on around us. Some of these can give like 180 degrees or 220 degrees. Some of them can give like 360 degrees right around us. And with angular precision of between half a degree and a degree or so, depending on how expensive the LiDAR is and what features it has. Now, the range of these LiDARs varies a fair bit, from short range ones that go up to only about 10 or 15 meters or so and are made for more indoor applications, to ones that might do up to 100 meters or so, that do those outdoor or longer range applications that you might need to use in things like autonomous driving or building reconstruction. Now, essentially the way we get data out of these things, we get data back as a whole series of individual decimal values. And each of those decimal values will represent the distance away from the LiDAR to the object that it's hit at each of those angles. So we'll start with maybe 0 degrees and go 0, maybe half a degree, 1 degree, 1.5, 2 degrees, or whatever it is. We can often program what our sensitivity is going to be and scan each of those. And we'll get like a RS-232 or a USB connection or a CAN bus connection or something that transmits all that data as a serial string to us and says, okay, distance is 10.1 meters, 10.5 meters, 10.2 meters, and we go through that whole arc between maybe 0 and 100 degrees, or 0 and 180 degrees, or 0 and 360 degrees for one that can go right around. Now, these 2D LiDARs aren't perfect. They have some problems with them. One of them is the limited scanning speed. If we've got fast-moving objects, 10 hertz might not be fast enough to scan with, and so we might need a faster LiDAR to actually give us that detail. Shadowing is another problem we can have. For example, if you can see in the picture here, if we're scanning and there's another object behind the object that we can't see, well, that's been hidden by our LiDAR makeup because it can't see through things. It assumes that, well, there's a solid object there and it can't see anything beyond that. But when we get up closer to it, we realize, oh, there's all this free space behind that object. And that object might be as thick of a sheet of paper or something like that. It could be quite thin. But according to the LiDAR, it seems like a solid object that's immovable and can't be gotten past. Now, they have a narrow beam width, as I mentioned, and that's great for characterizing things in that 2D plane as we move around. But what if we had some slats or something that went like this, and your LiDAR might be just at the right angle and hit one of those slats and it says, oh, there's a solid object there that we don't want our robot to drive into, or when we're trying to create our 3D reconstruction of the room, it actually picks it up. But what if it goes in between the two slats? and says, oh, there's nothing there. It's a void, and it goes whatever's behind there, maybe a wall a meter or two behind there. So that's something to be aware of with this narrow beam width. It can be an issue. And some of the robot vacuum cleaners, depending the height of that LiDAR, if it's not high enough, it might not detect a couch and then drive straight into that couch and clip the top of the LiDAR underneath the couch as it's going under, for example. And finally, the surfaces do need to reflect light. I talked to a guy who sold a whole lot of LiDARs in the past. He worked at a company that developed these sort of things. And he said at times when they did their technology demos, people with black pants would trip these things up because the black pants, if they didn't reflect enough light, the AGVs, the robots they were operating on, just didn't see the people with black pants, and it became a bit of a workplace hazard. Now, one thing that these LiDARs can be used for safety applications is a laser proximity sensor. And what they can do is they can be divided up into zones. Like, remember we had that 0 to 180 degree spread? We might say we don't want people in this zone, or we want to be alerted if there's people in this zone. We don't really care about that zone, and maybe we need to be alerted about this zone. And we can actually program in steps that if someone enters this zone or an object enters this zone, we slow down our machines, or we stop our machines, or we flash a whole lot of lights, or we call a supervisor over, or something like that to make the area more safe. So these can be used for these detection purposes and safety purposes on maybe a factory floor or something like that. Now, I mentioned these LiDARs before, these 2D planar ones, and they're typically quite expensive. We're looking at over $1,000 for this assembly where it moves the mirror around and reflects back. Having said that, there's some lower cost versions that have been produced more recently that are more aimed at the consumer market, because not many people have a budget to spend $2,000 on a robot vacuum cleaner because it's got a 3D plane or a 2D planar LiDAR in it. So the most expensive part of these 2D LiDARs is essentially the time of flight sensor in there. That needs to be super, super accurate, but the circuitry behind it's quite expensive. Well, what if we could sacrifice our accuracy a bit, maybe for some of those more consumer applications, but have a 2D LiDAR where the accuracy is not so stringent, but the cost is significantly lower? And that's actually been done. Neato was a Silicon Valley startup company. They developed some robots for vacuuming people's houses. And the idea, what they were trying to do is create a LiDAR in the order of $30. So those previous ones I was talking about are in the order of $1,000 to $2,000. Well beyond the range of a standard vacuum cleaner integration within a robot sort of system. So they created this low-cost laser distance sensor, and basically it allows a robot vacuum cleaner, here's a picture of one here, this is a robot that I've actually got and used around the house, to map out a room, see where obstacles are, and create a trajectory that is ideal within that area. And they published as an academic paper as well, so we can understand precisely how it works. They compare it to something like the early Roomba robots that just went around in random patterns, maybe tried to go around in circles and then just bounced off objects, that they can have a smart path that goes back and forward and vacuums the whole room. And the way this is done, and these are commercial modules that you can buy these days, and they're about $200 odd compared to the $2,000 or $1,000 for those time of flight based LiDARs, is a triangulation system. Similar to our triangulation sensors that we looked at previously, those little sharp ones, but a whole lot more accurate than them. So here they've got a little laser, and they've got a little module that reads the position of that laser as it bounces off things. So rather than having a pulse of infrared light that's fairly large, here it's a fine laser, and they have pretty fine angular resolution, so 0.225 degrees angular resolution, an accuracy of about 1 to 2%. And they actually just spin this thing. So they've got a little motor and they spin this thing and just rotates and moves around and takes all these measurements as it goes around. Now, I mentioned before that these the aim was to create these at about the $30 price point. Well, that's the price point you get if you made it yourself. If you buy these off the shelf, they're obviously more expensive. Now, I've talked about 1D LiDARs. I've talked about 2D LiDARs. Well, what about 3D LiDARs? Now, what you can do is you can get a 2D LiDAR and you can put it on a movable platform and do this with it. And you can scan a 3D plane and take successive points and create this point cloud in 3D. That's one way they have been done, and one way they've sometimes done for example, when we're mapping a building or trying to create a 3D model of a facade of a building, that we do that. Another way we can do it is get a solid state 3D LiDAR. And here's an example of one here. This one's made by Hypersend, but there's others around as well. The depth of accuracy on these is about 2 centimeters, so not super accurate, not as accurate as some of the other ones, but it does use time of flight. Now the cost of these isn't huge, about $350, and it gives you 160 pixels by 60 pixels. So 160 in the long dimension, 60 pixels in the short dimension. And it gives you a point cloud. So it basically tells you for each of those pixels what the distance is from the LiDAR to the object that it's sensing. So here's some example here with people within that range of the LiDAR, and the color there signifies the depth, so how far away those people are from the LiDAR.